Hi, this is Ken Johnson for another episode of SecCast. In this tutorial, we discuss and demonstrate logic flaws. We will discuss both business logic flaws as well as functional logic flaws. Logic flaws are, simply put, the manipulation of application functionality that causes some unintended result. Usually, that result provides a malicious user with something they want. It could be access to privileged functionality, a discounted item, or free piece of merchandise. When we discuss logic flaws, I'll separate them into two distinct categories: business and functional logic flaws. Business logic flaws occur when logic that is specific to the purpose of the application can be manipulated for personal gain, whereas functional logic flaws are more generic flaws in the application security mechanisms, like access control. There are some key factors in determining how to identify and exploit business logic flaws. Those factors are: what is the application's primary business purpose? What was it really built to do? Where are the key points in the application's flow that are critical to business? Is this an e-commerce site? Is this a data warehouse application? Review the flow of this functionality, see how the application works, identify key points for analysis. Attempt to perform this functionality in unconventional ways. Circumvent the native intended way the application expects a user to behave, tamper with parameters, etc. Here we have an application that is intended to allow members of this particular financial institution to submit applications and allow them to receive approval for loans. This is its primary business functionality. We'll authenticate as A. Smith, a user of the application who would like to request a loan. We're going to submit a loan request for $1. We fill in the appropriate information and save our application. Next, we log out of the application. Next, we authenticate as J. Rogers, who is a loan approval officer. We'll navigate to the list of applications that have been submitted. You can see in the Action button we have a few options. We can edit or remove the application and approve or deny it as well. At this point, we will copy the URL for this application list and log out of the application. We once again authenticate as A. Smith, our user who wants a loan for $1. Let's copy and paste in that URL and see if we can't forcefully browse to the endpoint. We can see our loan in the list of loan applications. It appears they are not properly validating our role on this page. Let's go ahead and approve our request. It worked. The vulnerability is actually in the access control mechanism, and we use forceful browsing to attack it, but we are in essence attacking a very important piece of the business logic within the application and circumventing its intended use. We want to find multiple ways to exploit this application's clear lack of access controls, so once again, we will authenticate as A. Smith and submit a loan request. This time, we will create a request for $100. Pay attention to the status field, which has the number 0. This might be of interest. We save and submit the application, but before it reaches the web application, let's first inspect the traffic. We once again see the status code field set to 0. What happens if we change it to 1? We can see that our loan, instead of going through the proper approval process, was approved by us simply by changing the status code. The last thing we will try is to submit an application as an actual loan approval officer and see if we can't find a way to approve our own request. This is not something that is supposed to be allowed, as another loan approval officer should be reviewing our request. It makes sense, as otherwise we'd have the ability to give ourselves money without any oversight from the business. We will authenticate as J. Rogers, a loan approval officer, and navigate to the loan application page. We will submit a loan application for $100,000. Next, let's navigate to the View Application Queue page. Note that our loan does not have a button that allows us to approve or deny the request. This is probably a good idea, given that the application does not want us to approve our own submissions. Now, we can see some application ID values, 4 and 7, on the left-hand side. It appears a date was meant to fill this column, but instead an ID is. Must be a bug in the application logic. We will try and approve the other loan that is pending and see what the request looks like. Interestingly enough, we do have an ID value of 4 in this request. Our application's ID appears to be 7. Let's rotate this number 4 to 7. It appears while the visual components exist to deter us from approving our own loan request, we can still circumvent that logic using insecure direct object reference and approve our request of $100,000. Looks like we are going to have a very fun weekend. Functional logic flaws are fairly straightforward. Identify key parts of the application that could be important from a security standpoint. This could be authentication related, access control related, or session management related, but the idea is that anything that prevents us from being malicious should be examined. Finally, as we mentioned previously, attempt to perform this functionality in unconventional ways. Here we have an application whose authentication mechanism is split into two parts. The first part requires a valid CAPTCHA and username. The second part requires a password. The goal of the application is to make it difficult for us to guess usernames and passwords and ultimately to prevent brute force password attacks. A noble cause. We've identified a critical security feature. Now let's circumvent it. First, we enter our username and then a valid CAPTCHA value. After successfully completing this step, we are prompted for our password. We enter our password and intercept the request in our local proxy. Let's send this request to intruder. You can see that even though it appears to be two separate steps, the username and password values are aggregated and submitted as one large authentication request to the application. Ouch, this nullifies the original intention of this control altogether. We will place an insertion point around the username since we want to rotate this value iteratively as we try out different usernames. We navigate to our payload list and select usernames. Additionally, we'll add a username jdoe, which we know does exist on the application, just to make sure that we run through about 8,000 usernames before hitting the right one. If we are able to authenticate, we can prove this application is vulnerable to brute force credential guessing campaigns. We'll bump our thread count for speed, start the attack, and let it run. After completing, you can see that while the majority of the guesses resulted in 200 response codes with a byte length of approximately 3400, jdoe results in a 302 response code or redirection with a response byte length of 914. If we take a deeper look at the response, we can see that it redirects us to our homepage. This is a good sign. We will navigate back to the request that is still stuck in our intercepting proxy, change the username value from tester guy to jdoe, and send the request on. And you can see that it worked. We've proven that the multi-step login flow is fundamentally flawed. We've covered both business and functional logic flaws. While we cannot possibly present you with every scenario where you might find these problems, we hope that you've begun to shift your mindset to that of an attacker. When analyzing an application, you want to circumvent controls and cause unintended results. I'm Ken Johnson. This has been another episode of SecCast. Thanks for watching.